Okay, so now we're looking at electric potential. We've looked at the electric field, which helps us figure out what the force is on a charge. The electric potential is more related to energy, right? So we looked at electric field for forces. We look at electric potential for more about energy, and we'll also learn that we can relate those two pretty easily. All right, so for work, right, we start, whenever we're talking about energy, we usually start with talking about work. If we're in just one dimension anyway, when we have a constant force, the work done on an object moving a distance d is what? Does anybody remember? If I just have a constant force.
Force times distance.
Force times distance, right? The work is just equal to that force in the x direction times the distance d. So if I'm going to plot that, right, or on the I can graphically represent that force. This is a constant force. How would I represent the work done on this graph here?
You take the integral.
It's the integral. So on a graph, what does that look like? The area, right? So the area under the curve here is the work, right? And whenever you have a force plotted against a distance, the area under that curve is going to give you the work done, right? So that's for a constant force. It's nice and easy, but with our electric forces, we know they're not constant, right? Because the farther you get away from a source charge, the weaker the electric force is going to be. All right. So when the force is not constant, we have to break the path up into a series of small steps, and then we add up the work that we do on each step. All right, so the work there is going to be a sum. So it's going to be a sum from, say, our initial x, we'll call x0, to our final x. We'll take our index n. It's going to be that sum of the force of at each of those steps times delta x, which would be how wide the step is. So in particular, we're going to look at the work it takes to move a positive test charge, q. So we'll put our source charge here, or a test charge here, from a long way away, so basically at infinity. And we want to bring that into a distance r from our source charge q. Right, so we're basically moving from it here out in infinity. I didn't really draw this an infinite distance away because the paper's too small. Over to q, or over to x equals r. Right. So just maybe you can remind me, what's the force going to be at any given point x on the test charge, right? We're using Coulomb's law. What is Coulomb's law?
K times Q times the other Q, the test Q.
Yep.
Over the distance squared.
Yeah, over the distance squared. In this case, our distance is just x, right? We're just looking along the x-axis, one dimension. Right. So yeah, so that's going to be our force there, right? And I've plotted here already the shape of that force, right? It's 1 over x squared, which looks something like this, right? So if we want the work done as we go in from infinity to r, right, we need this area, right? This area here is the work, right? And it's not as easy as up here where we just multiplied the force times the distance, right? That's a simple calculation. That's a rectangle. Finding this area is a little bit trickier, right? So that's why we're saying we have to break it up into small steps, right? Here, each step here is a width delta x. And the height of each one of these would be the force at x, right? And then we just have to add them all together. Right, so the idea to find the area under this curve is break it up into a bunch of rectangles, right? Because we can find the area of each rectangle will be the force times delta x, This area will be this force times delta x. This area will be this force times delta x. And if we add those all together, we get our total work done. Okay, so far. So at this point, I know a lot of you haven't done integration yet in your calc classes. Those of you that are just taking calc now. So this is a real brief introduction to integration and the fundamental theorem of calculus. Right? This is what we need to do is to be able to find out area when you're integrating, you're finding the area under a curve. So the approximate work done, right, or what we get by adding up the work done by each of these squares, right, that's going to be the sum where we take our index from our initial to our final x. Of the force at each point times our delta x. And we already said what the force was at each point. Right, so that's going to be the just trying to think about the best way to do this here. Yeah, so that's fine. So we'll go and say that the approximate work done is going to be the sum over each of these squares of k, q, q over x squared times our delta x. So each of these rectangles, the height is kqq over x squared, and the width is delta x, right? So when we take the sum of all these, we get the approximate area under the curve, which is our work done. Okay, so, but that's not going to be good enough. That's just an approximation. What we want is an integral, right? So to find the exact amount of work done, we have to basically take the limit. You can see that if we shrink the width of these rectangles, right, the closer we get to 0, the smaller we make these rectangles, the better our approximation is going to match the area under that curve, right? If I make these rectangles infinitesimally small, then the area we get when we add up all the rectangles is going to equal exactly the area under the curve. So really, we need to take the limit of this sum as our delta x goes to 0. And what happens there is that the sum becomes an integral. Right, so this sum limit in the limit that x goes to 0 of the sum from x naught to x final of our say f of x delta x, that turns into this integral. And if you haven't seen integrals before, what we call these two are the limits of integration. Basically where we start and where we end, right? So from, well, we're really going from here to here. And this dx is what the delta x turned into. That's the variable of integration. And the way we work out what the integral is, it's actually, if you've done calculus so far where you're able to do derivatives, you should be able to evaluate these integrals as well, because we just use the fundamental theorem of calculus, which says that an integral from any limits a to b of any function f of x dx is just equal to this function f evaluated b minus evaluated a And that big function capital F is any antiderivative.
Does that symbol, like the integral symbol, does that say xf approaching like x0 or as it approaches x0?
This one?
No, the integral like symbol,
This,
like next to it.
this is saying the integral this one up here.
Yeah, I meant that one. Yeah,
So
sorry.
this one we go, so basically our starting x to our final x. So the way
Okay.
we've looked at it, when we're doing our work, right, or when I phrase this problem, we're looking at the work it takes to move a test charge from a long way away, or infinity, right? In physics we call infinity a long way away, infinity, into a point of distance r. So in this case, we're going to see our limits are going to be, we're going to start out here at x equals infinity, so our x naught would be infinity here, and come into x equals r. So we'll see our second limit here is going to be r.
So the bottom is where you start, and the top is where you end up. Okay.
Yep. And it's probably a little confusing to start out at infinity and come into r in this case, but you can go in either way. All right.
Yep.
And an antiderivative, I'm not going to go farther into that. Just any function. So if capital F here is an antiderivative of our original f of x, that just means if you take the derivative of this capital F, you should get the original function that you started with. So if you know how to take derivatives, you can also do integrals because it's just basically backwards. All right, and you can probably help each other out. Those of you that have taken calculus can help those of you that haven't done any integration yet as we go along and do this. But that's as much of the calc lesson as I'm going to give. But now that we know this fundamental theorem of calculus, we'll do it as an example. We'll find out what that work done on our test charge is. All right, so let's work that out. So let's see, let me go back up to this, right? This is the work done, this is the approximate work done. I want to write this sum now as an integral so that we can get the work done. Exactly. So rather than the sum going from x naught to x final, let's specifically look, just like Harris just asked, we're starting at infinity here. So that's going to be my lower limit of integration. And we're coming in to x equals r. So that's my upper limit of integration. The force, let me...
We can't see, by the way.
Oh, I'm sorry. Okay, here you go. Let me go back up here because this is where I wrote down the force, right, that we just got from Coulomb's law. So this is I just want to change this a little bit because this is the force that the source charge placed at any point is going to feel being repelled away from the source charge, right? If the source charge and the test charge are both positive, the force is going to be to the right. But if I'm the one that's doing the work by pushing in the source charge, what direction would I have to then push to do the work to counter the electric force? Not to the right. Yep. You're going to say something, Ellie?
Me? No, I wasn't saying anything.
Okay. So I'm going to make this negative because the force it's going to take to bring the positive charge back in is opposed to the electric force. All right, so we have to push the other way, so that's going to be negative. So when I'm down here at my work, I'm going to say it's negative k q over x squared.
Can you move the top paper a little bit up?
Move oh yeah.
Thank you.
All right. So this is the integral that we really want to evaluate here to get our work done. And when we the first thing I'll do is take all the stuff that's constant out of the integral. Makes it easier to see. So I have minus k q q, minus k q q times the integral from infinity to r of x to the minus 2, right? Because it's 1 over x squared dx. So I think at least some of you, most of you can, or the ones that have taken calc, should be able to evaluate this integral. Right? What function, when you take a derivative, would give me x to the minus 2?
It's cubed. Or x to the negative 3. Or
Is that right? If I take
no. It's x to the negative 1.
Yeah, x to the negative 1, right, would be the antiderivative. Because if I take the derivative of x to the negative 1, I'll get negative x to the negative 2.
I have no idea why I said x to the, I don't know, it's been a while, mister.
Yeah,
It's been like
that's
6
fine.
months or something.
That's fine. That's fine. So what we get, so it's going to be, when we take the antiderivative, there's a minus sign as well, right? Because if I want x to the negative 2, I have to have negative x to the negative 1 to get the derivative to be x to the negative 2. That negative sign cancels out with this negative sign, so we just get k q q times x to the negative 1, evaluated then at infinity and r.
So I kind of forgot, mister. What do you do with the infinity?
So let's see. So this is the fundamental theorem of calculus, right? So we want to plug in the r value here, and we also are going to plug in the infinity value here and subtract, right? So what we get when we evaluate, and you'll see what happens to the infinity in a second, is k q q times we x to the minus 1, that's 1 over x, right? So that's 1 over r minus 1 over infinity. Right, and 1 over infinity is pretty easy to evaluate, right? 1 over a very big number tends to go to what?
0.
0, right? So we can ignore this, right? Because because this is just 0. We have no problem doing 1 over infinity.
Wait, Mr.
Yep.
I still don't understand why it's negative force.
Oh, because okay. Yeah, that's a good question. So we're not saying the work. So we're not saying the work is done by the electric field here, right? We're not talking about a charge that's being. If I put a positive test charge here at x equals r and just let it go, the source charge is going to push it off out to infinity, right? It's going to be out. But if I want to, but I'm saying how much work do I have to do if I want to take that test charge out here and push it back into here? So to overcome the electric force, I have to do work in the opposite direction.
Oh,
So-
okay.
Right. So the
So
minus
saying that-
sign, yeah, go ahead.
Oh, sorry, no, you go ahead.
So the minus sign is really because we have to push against the electric field, right? The work we're doing comes from a force that's opposite to the electric field. Does that clarify things?
So does that
Yeah.
mean that the charge is negative?
No,
Sorry,
in the
positive,
charge is
the test
negative.
charge.
Yeah, so, well, we're seeing now we've defined our test charge to be positive, just q, right, this lowercase q. Everything would still applies if our test charge is negative, there's just another minus sign in there, right? For a positive test charge, we're going to have to do positive work, right, to push it towards another positive test charge. But for a negative test charge, we would have to do negative work, right, because it's going to be naturally pulled in towards the source charge. So if we wanted to, we could do negative. So it would be negative work if we wanted to do that. Good questions. Okay, so we basically have the work done here, right? So the work done is on our test charge, right? The 1 over infinity right, is just 0. So really the work is just K times,
We can't see your paper.
sorry, work is really just K times both Q's over R. Okay? So that's how much work it's going to take in order to bring that positive charge over in to x equals R. And that's also going to be the same amount of work, right? Equivalently, that's the amount of work that the source charge would do if you put a test charge at R and let it zoom out away to infinity. So this still needs to be related to the electric potential, right? And also to energy, right? We said electric potential is related to energy. So here's where this kind of ties together. We're almost done. So from conservation of energy, we know that the work done on the system when we move the charge is going to be equal to what? What does conservation of energy tell us the work done on the system is going to be equal to?
The negative potential energy.
Yeah, well, pretty close. Is it going to be the negative? Well, it's going to be the change.
Well, if we're talking about like electronics and such, then it's going to be the voltage, right?
We're getting there. We'll get to the voltage. It's not the voltage doesn't have units of energy. It's equal. So it's going to be equal to the change in energy of the system. And you're right. It's going to be potential energy. Right. That's just that's a general statement, right? That's conservation of energy. If you do work on a system, then that work turns into energy in the system, right? That comes from our change in energy is just equal to the external work done. The type of energy that we get, and I think it was Harris that just said it, is what type?
Potential.
Yeah, potential, electric potential energy, really. Right, so in our example here, the change in UE, right, capital U for potential energy, the E to denote that it's electric potential energy, is then the work that we did, which we found was K Q over R. Right, that's for our example. In general, right, might not just be a single charge moving in from infinity to 0. In general, we see that the potential energy is the integral from our starting point A to our ending point B of whatever the force is times dr, where that's the path that we take. I didn't prove this one to you, I'm just doing the one example, but this is the general statement for it. Okay.
Mister.
Yeah.
Shouldn't it be negative? Do that.
We had this, the work done was positive, right? Because we had a negative force, but then the antiderivative of x to the -2 gave us a minus sign, so that we ended up with a positive value here for work. We gained potential energy.
But shouldn't the potential be the opposite of work?
No, because the work if we do positive work, then we increase the energy of the system. Right, so the potential energy goes up because now we have more potential, right? When we've done that positive amount of work, we have that. Now we have the potential. If we let go of that test charge, right? Now that potential energy is gonna quickly turn into kinetic energy as it's pushed away from the source.
Okay.
So we're almost there now. So what we're going to do here is, remember how when we defined electric field, the point was we can divide out the value of the test charge, and the test charge we say doesn't even matter anymore. We can put whatever charge we want in our electric field and it'll feel a force. We want to do kind of the same thing with our potential energy. We don't want it to depend on the test charge. We can find out if we just have a source charge placed somewhere, we can put any charge there and figure out what its potential energy is going to be. So what we do is if we divide by the test charge Q, we obtain a quantity that depends only on the source charges or the source charge. There might be more than one. And then we'll define that quantity to be the electric potential. The symbol we use is capital V, the electric potential or voltage. And that's just our electric potential energy divided by our test charge. And this is called electric potential. So potential and potential energy are different things, right? Sometimes this is called voltage. And the unit for that, easy question, what's the unit of voltage?
Volt.
Volts. And you can tell that we define a volt here, right? As, well, what's the unit for energy or potential energy or any kind of energy?
Newton meters.
Coulombs.
No?
It's
What?
Newton meters, right?
It is
Newton meters per
it is
second.
Newton meters. It is Newton meters, but
Newton meters squared per second?
there's another word for Newton times meter.
Oh, is it with a K?
Nope.
Oh,
Work.
Come on, the SI unit for energy.
Joule.
Joule.
oh, there.
Joule. I know everybody knew that and just couldn't think of it. So the joule and the unit for the charge.
Joules per coulomb.
The unit for charge is just coulomb, right? Oops, I'm spelling that wrong. Right, so a volt is just a joule per coulomb. Right? Or a Newton meter per coulomb, or right. There's a few different ways you can write it, but this is the easiest way to see based on this equation. So it's how much energy, how much potential energy a test charge has at a particular point.
Is there like a particular reason why you're putting 3 lines for that, like for the equal
Yeah,
sign?
right, because that's the symbol for definition, right? It's more than just equal to, I mean, it is equal to so the potential is equal to the electric potential energy divided by the charge, but that's how we're actually defining it.
Right.
So it's more than equal, it's actually the definition. So for our point charge, our point charge example, we get the potential is equal to, oops, sorry, I'm making a mess. What we have here divided by our lowercase q, right? So that just means we divide this q out and we just get K times the source charge over R, right? Which ends up being a pretty simple, value to work out. It's similar to the electric field, right? Except it's not R squared, it's R, And there's no direction. Potential is a scalar value, so we don't have to worry about the r hat, which is nice when you're solving problems. In general, right, if I go back up to here, what do I get if I divide, there's a quantity that we already know, if I divide the force by the test charge? Which quantity is that?
Electric field.
Yeah, electric field, right? So I can write, so if I take this, if I divide this by the test charge, the force just turns into the electric field. So in general, my potential is going to be, I'm going to need a negative sign. From my first point to my second point, point A to point B, the electric field times your dr. And I'm going to I have to put the negative sign back there, because remember, this force was the force we had to push against the electric field to do our work. So I had put a negative sign in there, and now I have to put the negative sign back. I'm sorry, that's a little bit confusing. I should have thought that through better. So a couple quick notes, and then we're ready. Then that's about it to end. So the convention we usually use, the potential is going to be 0 very far away from a source charge. Or at infinity. Right, we found here the difference in potential, right, delta V. But if we're just looking at what is V, we use the convention that at infinity our source charge is 0. And that's equivalent to saying, when we're talking about just in a gravitational potential energy, MGH, right, we need to pick a height that's our 0 value for potential energy. Usually we pick the floor or the table if you're doing a lab. Here the convention is the potential is 0 once you get very far from the source charge, so at infinity. And we'll see when we're going to look at visualizing some electric potentials, and we'll see why that makes sense when we do that. The actual value of V is not physically realistic or physically important. Only the difference in potential is important. So only the difference between 2 points. And that's true for any sort of or potential energy as well. And finally, the superposition principle holds for potential as well. So 1, 2, and 3. The superposition So that means if you have more than one source charge, you can find the potential because it's the sum over each source charge of K times that source charge over its distance from the point we're looking at. Okay, so that's it for the potential lecture today. Does anybody have any questions about what we just saw, what we just heard?
Yes. So we did volts, but what about the electric difference, electrostatic difference, or something like that? I forgot exactly what it was called.
The electric potential difference, I think, was what was the problem that we were doing yesterday, right? That you referred to.
Right. Yeah. So how would we find that?
That's the so this is the potential difference, right? Because it's got a delta, right? It's the change. that we get it from going between 2 points, right? In our case, in the example case, we were going from infinity to the point R. You could say that what we are saying is that the potential at infinity is 0, right? And that's because KQQ over infinity is going to be 0, right? And when we get to point R, it's just KQQ over R. So really, it's the potential difference. It's the difference between, KQQ over R and 0. So we're really just subtracting the 0 because we're coming from infinity. So when you see electric potential difference or electrostatic potential difference, it's just voltage. It's the same thing that we're talking about here.
Okay.
And that's what we ended up working through and finding in the problem yesterday. I think we used this equation pretty much as it is. Does that answer?
Yeah. Just all these names confuse me.
Yeah, you're right. It's confusing that I know I used to get confused between electric potential and electric potential energy. It seems like those should be the same thing, and they're close to each other, but they're not, right? Because one has divided out the test charge potential, but potential energy doesn't have the test charge divided out.
Right.
Good questions. Anything else about the lecture here today? I did remember to record it this time, so I'll put this up on YouTube again, so if you need to refer back to it.